When performing numeric computations on digital computers, we should always keep in mind the limitations of hardware's precision and capacity in storing these numbers. There are three kinds of errors that may occur. The first is when the rounding errors accumulate. Rounding error is the difference between the rounded approximate and the actual value of the number that we wanted for the computer to represent. The second is an overflow, when the number is too large for the computer to represent. This may result in the number being approximated as infinity, or minus infinity, or may even result in an absurd sign change. The third is an underflow, when the number we want for the computer to store is too close to zero. Due to lack of precision, the computer will truncate the number to zero, which may later result in an error in attempt of dividing something by zero. We will now consider these issues in more detail. On this slide, we will consider the rounding error, which occurs when we want for the computer to store the number 0.1. To store this number, we will use the Python variable float and C++ variable double. However, the same error will be encountered in every programming language. By default, the programming languages will not show you the entire representation of what they have in memory. On this slide, we specifically request for them to show us the 55 digits after the decimal point. As you can see, instead of 0.1, the digital computer stores an approximation that is slightly larger than what we wanted. This rounding error may appear to be too small for it to have any effect, but we will now show how critical it can be. On this slide, we simply add an approximation of 0.1, 2 million times. The error that appeared minuscule has now accumulated to be greater than 0.1. Depending on the task we are assigned, an accumulation of rounding error can be fatal. For example, it was due to the accumulation of rounding errors that in 1991, the Patriot missile battery failed, resulting in death of 28 soldiers and 100 injured. Let's now consider an overflow. The upper codes you see on the slide ask Python to store 10 to the power 450 as float, and C++ to store 10 to the power 450 as double. However, the value is too large, so an overflow occurs in both programming languages, and the value is approximated as infinity. The other kind of overflow occurs when working with integers. For example, a signed integer variable in C++ can only store numbers between approximately plus and minus 2,147,000,000. The code on below left adds two positive numbers in C++, but you can see that the result is negative. This, however, is easily solved by using other kind of variable with larger capacity. Python, by default, uses a variable with an arbitrary capacity. An underflow occurs when the number we want for the computer to store is too close to zero. Due to lack of precision, the computer will truncate that number to zero. The upper code you see on the slide asks Python and C++ to make a float and double variables respectively, and store 10 to the power minus 450 in them. However, the value is too close to zero and is truncated. We can see that C++ even gives us a warning about it. We should be very careful when working with such numbers, as they may result in absurd results, or divisions by zero. This concludes an overview of different kinds of errors that can occur when performing computations on a digital computer.